example for any other.
All right, ladies and gentlemen, class recording has started. So, plan for today, I wanted to go like this. One, I wanted to finish up the stuff on light and color that we started on Friday, but we did not finish. Then I'll tell you about the test in general, and then you guys can ask questions about the test and go from there. So, if you do not have the slides from Friday that were titled Color, please pull those out, and we'll finish those up, and then we will get into stuff for the test. Okay, so I know I asked you guys to fill this in over the weekend. Hopefully you had a chance to. Even if you did, we'll get a chance. We'll go over it real quick just to make sure that we hit the high points and stuff like that. So. You can just listen attentively. All right. So, color comes from visible light, which we said was one form of electromagnetic wave, or one small portion of the electromagnetic spectrum. It's actually a real small sliver of the electromagnetic spectrum. But within that category that we call visible light, there are different wavelengths. And those different wavelengths are interpreted by your eye as different colors. And I think that we've probably all seen this before, yes? Okay. That this idea of a prism, where you may not have actually seen it in prism, but if you've ever seen a rainbow, or if you've ever seen, like in the summertime, if you just take like your hose and kind of spray it into the air and you can make yourself a rainbow like that, right? You're seeing this idea of what we call dispersion, okay? So first, let's zoom in on one little section of this picture up here, this picture of the prism, okay? And let's talk about this little section right here. All right, so first, light's coming in, just like this, okay? And it looks white. What did we say that white light was? Or what did you learn from the video that white light was?
All
colors. It's all those different colors all together, okay? That in the video, right, even though we didn't see a whole lot of the video, I think we saw at the beginning of the pinball game when Miss Frizzle shoots the light pulse and it goes through the prism and it splits up into all the different colors, right? Okay? That white light is actually a combination of all those different colors. So, first, here, what do you see happens to some of that white light when it hits the prism?
Some of it reflects.
Some of it reflects. Remember we said that anytime there's a boundary between two different mediums, some of that wave is going to reflect off the boundary at the same angle that it comes in at, right? Yep, same speed, same everything, okay? And that comes off as white. But if you look down on the other side, right, over here, now we start getting some color stuff coming out of there, okay? Yes, sir?
What about that light at the bottom?
This light here?
Yeah.
What we're seeing there is that, actually, Eric, we're going to zoom in a little bit, and these waves kind of come through here like this, and as they travel through the glass, now when they hit the other side, some of it reflects back again. Right? Some of it reflects back again, some of it goes through, but then what we're seeing here is the stuff that's coming out after what we call the internal reflection. Okay? But that's what that part is down at the bottom. And that happens all the time, because any boundary between two mediums, we get some reflection and then some transmission, where the energy will go through it. But we also discussed that what happens generally to waves when they go from one medium to another? They change what? They change speed. Okay? No, not the same thing. Okay? So, could you put it back together? Hold on one second. Let's finish this, and then we'll talk about the other prism. Okay? So, change speeds. But we also said that change in speeds generally comes along with what other wave behavior that we talked about. The change in speeds causes what?
Amplitude. Change in frequency.
causes
Dispersion.
refraction. I did not hear you say that. I didn't hear that. So, as the light wave passes from one medium to another, the speed of the wave changes, and that causes refraction. And that causes light waves bending, right? So Eric, if we go back to our picture, right? These light waves that come out over here, the different colored ones, they're not going in the same direction that they were originally going in, right? There's that change in direction as we go through this medium. But what we find out is that different wavelengths of waves will bend by different amounts going from one medium to the other. This is true of light waves, but it's true of any waves. So even sound waves that have different wavelengths and different frequencies will bend by different amounts when they go from one medium to another. Or water waves, if they go from one medium to another, if they go like from deep water to shallow water, stuff like that. All these different wavelengths of waves will bend by different amounts. What does that mean? That means that when we go here, these colors come in all together as white light, but they bend by different amounts. Red has a long wavelength, which means it has a lower frequency. It bends the least. But violet has the shortest wavelength, meaning it has the highest frequency, and it bends the most. And that's why they always come out in this order: red, orange, yellow, green, blue, violet. Because that's how much they all bend differently as they go from the one medium to the other, and that's why they end up separated now. They were all together, but because we bent them different amounts, we basically, it's kind of like taking a fan, right? When the fan's all squished together, like not a circular fan, like a hand fan, right? When it's all squished together, it all looks like one thing, but then we spread them all out, and now we can see each of the individual parts of that fan. And that's pretty much what we're doing with this idea of dispersion. Okay? Eric, question? Are you good?
No, I'm just saying, like, we learned about Roy G. Biv, and there's no indigo.
Right.
Is that...
Indigo's kind of went the way of Pluto, you know, like, because even when I looked at it, I'm like, that really doesn't look any different than purple to me. So, you know, but I mean, it's still okay because, you know, even if you just get rid of the I in there, it's still Biv, you know, so you can still go Roy G. Biv. Okay, so is that good? Anybody else have a problem with that?
They taught us wrong.
Yeah. Take it up with like the National Physics Board or whatever. You know, so. All right. So are we good with this idea of dispersion? Okay. And this is what happens when rainbows occur. Okay. What happens there is that the water droplets end up splitting the light apart into its different colors, and that's why we see different colors. Rainbows are a little bit different. Rainbows actually come out. You don't see rainbows on the other side of the prism like you do in this picture. The light actually bounces off the back of the water droplet, so the sun has to be behind you for you to see a rainbow. Yeah, just keep that in mind. You're looking at it. So, okay, yes.
Why does it appear to bend?
The rainbow?
Yeah.
That has to do with the light. When a rainbow gets made, it actually is a whole circle, but we don't see the whole circle because the ground gets in the way. But if you can, totally. So, you know, a totally circular rainbow would be awesome. So, yeah, it's like, I don't know if it's like all around the whole Earth, but it is like circle because you're going through water droplets, so that it gives it that round shape and stuff like that. So yeah, we just get like the one part of it because the stupid ground gets in the way.
Oh, because that's
So
like...
there is a rainbow's end, like you can actually, can you see it?
No, because actually it's a circle.
Right, I know that,
It goes
but
into the
if
ground.
it goes into, you can see where
It really doesn't go into the ground.
I know, but like, can you, if we're setting
If
up a
you
full
walk
circle, then
towards it, you're never going to get to the
why
horizon.
can't you, like see it before?
Where does it end?
Doesn't circle? What?
Where, she said it goes to the ground.
No.
Yeah, no, you
It's
said the
a
ground's in the way. So
Right.
like, this is the ground,
Yeah.
and then this is the rainbow. Can I go here?
No,
Why?
because the rainbow. So it's here. So
So I can pick it up.
this is the rainbow. Okay. Does that make sense?
No.
The rainbow isn't
It's
on
not
the
like
ground.
resting
It's
on
in
the
the
ground.
air.
It's like saying you could like go in the
So
ocean
you
and reach
can't
into
like.
the ocean.
It's like when you
So
see
like
the
the
tall
other-
building.
And you approach
Or if
it
you
as
go
you get
to
to
South
city, you can
Pole,
see
you'll
lower and lower
fall
on the building, and
into
as you drive
space.
away from it, you can't see the
Like,
rest of it.
yeah, like, so Sam, going back to your example, right? It's not like the tape doesn't come up through the middle of the ground. The tape's back
Oh.
here. This is where the circle is, but you can't see the end of the circle because the ground's in the way.
So it never touches the ground.
No.
So it's here, and then like it would be like out.
Yeah.
Think of a ring around the
Okay.
planet.
So it's like far
But
away
it's
from
not
the
Yes.
ground.
You just can't see you can't see the whole circle
We
because
have
the
a
ground's
picture
in
of a
the way.
rainbow in outer space.
Wouldn't people
Like,
at a certain angle on the Earth like only see like two ends? Wait.
Depending on where you are, you can see more or less of it. Actually, it was the best rainbow I ever saw. Actually, I was down in Texas, and I was driving in Texas, and it's seriously like it started on like one side of my car and went like all like you could see one side of it out of the driver's side window. You could see the other side out of the passenger side
Have you
window.
ever seen a triple rainbow? They're really cool.
What does it mean?
No, when you see like three rainbows like arcing over each other.
It's pretty.
Wait,
Yeah.
or like,
So-
I feel like one time I was going skiing at some point and there was like a sun, or there was the sun, and then
Sun.
Any sun.
no, it was like, I feel like there were rainbows like around it.
That might have to do with, like, were you like in the car? Or-
Yeah.
Okay, so it might have to do with like, if there was frost on your window or something like that, that might have had something.
I'm pretty sure we like rolled down the windows and got out of the car.
Yeah.
Water in the air maybe, but you usually have to be behind, the sun has to be behind you to previous year window, so. Alright.
No, I was wearing glasses.
Alright, so that light that you see, right, we said is really just white light. It's a combination of all the different colors of light. But there are certain things out there that will absorb certain colors of light and reflect other colors of light. And I think we talked about this kind of pretty extensively on Friday, right? Okay. That there's only two ways that you can see an object. What did we say has to be the case if you're going to see an object?
It has to be color reflective.
There
It has to be light.
has to be light, what? John? Reflected off of it. So that's one way you can see the object. Or the other way you can see the object is what? No.
Other colors are absorbed.
That's causing the reflection of the one of some color of light. So that's the moon, right? You can see the moon because light reflects off of it. What's the other big thing in the sky you can see?
The sun.
Why can you see the sun?
Because it gives off light.
Because it gives off its own light. So for you to see something, it either has to give off its own light, or some light has to reflect off of it. Now, depending on what light reflects off of it, or what light it gives off, that determines what color it appears to us. Right? So we said that this green leaf looks green because white light shines on it from the sun, and all the other colors get absorbed, but green gets reflected. So green is the only color that gets to our eye. Okay, Kaylee, go ahead.
Why do we perceive the sun as yellow then?
That has to do, there is a lot of yellow light that comes out of the sun. That the temperature that it's at, it does kind of give off more yellow light than other stuff. But it also has to do with as the light comes in, it goes through the atmosphere, it gets refracted and it does dispersion, just like we talked about there before. So that has to do with certain colors of light that get to your eye. Okay, so but there is a lot of yellow that comes out of it because of the temperature that it is. Okay, but here, Kaylee, that leads us to a good thing here. So here,
Wait, but why are the other colors absorbed and it's only green?
because Eddie, that has to do with the stuff that it's made out of. Okay, Eddie, you can go to the store and buy a shirt that's 5 different colors.
Yeah.
Okay, same shirt, 5 different colors. There's really nothing fundamentally different about that shirt except for the dye that was used to color the cloth. Okay? The dye is made in a way that it absorbs certain colors and reflects other colors. That's like the chemical makeup of the dye. And that's why it appears different colors. Because there's something about the chemicals that are in it, certain about the chemical structure, that absorbs those colors but reflects other colors. And that's why it looks purple or red or yellow or green. Does that make sense or no?
It's just like
does that, I mean, do you understand what I'm telling you?
Yeah.
Okay, that's what it is. So, it has to do with the dye that's made. You know, certain dyes absorb certain colors and give off other colors, and that's why they look red or green or blue. Okay, Sierra, go ahead.
In a leaf or
Yep.
whatever, what's the thing that makes it green?
What's that thing that makes leaves green?
Chlorophyll.
Chloroplast holds the chlorophyll, but yes, chlorophyll.
Well, wouldn't that give off the green?
Yep, and it does. But do you remember what chlorophyll is used for?
No.
Anybody?
Photosynthesis.
Photosynthesis, right? So in the fall, right, when photosynthesis stops because it's getting cold out and blah, 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 blah,
They turn a different color.
the chlorophyll goes away, it breaks down, and it's not in the leaves anymore, therefore they don't look green anymore.
That is so crazy.
Does that make sense?
Yeah.
Yeah. That's what, yeah, that's right. So, Kelly, back to you before. And so here's this. Alright. Nope, too far. Alright, so here's you standing on the good old edge of the earth. Okay? With, yeah, not to scale. Okay. So the sun's going down, right? So the sun's up, blah, blah, blah. There's some, you know, as the sunlight goes through the atmosphere, it gets broken up, right? Atmosphere playing the role of the prism here, okay? Different speeds, different wavelengths, gets broken up. But when there's a whole bunch of it, it all sort of kind of mixes back together. Except at what time of day?
Noon. Midnight.
When does the sun look different?
Sunset.
Sunset and
Sunrise.
sunrise. When you're here, right?
Oh,
Okay.
is that why the sky's blue?
So the sky is blue because blue and violet sort of get scattered around more than other ones because they have lower wavelengths, so they get bent more, so we kind of see them more. Okay? Except at sunset, because the sun is down here, and it's giving off light, and that light is hitting the atmosphere at a pretty severe angle now because the sun's going down, right? And so it's bending. What are the only colors that are getting to your eye right now?
Red,
Red and orange. Okay? Now, there's something else you have to consider. Okay? Remember that thing we talked about with the pool? And like, where's the fish or where's the diving ring in the pool?
You have to dive farther than where you
That when you look in the pool and you see the diving ring, it's not really there.
Yeah.
Okay? Here's red. And we trace it back. Ooh, that's not red. That's blue. Here's red. Right? And we trace it back this way. Okay? My picture's not the best, okay? But there's the sun.
That's not what it's called.
It's not where the sun is. So when it's down low enough where you're seeing like the red and the orange sun, you're not seeing the sun.
The sun's already like below.
It's already below the horizon.
Wait, so what are you seeing?
You're seeing the red light that's coming from the sun, but you're only seeing the red and the orange. You're not seeing all the rest of it,
Because it's split by the.
and because it's bending as it goes through the atmosphere.
So
So it's sort of like peaks around here.
Kind of.
sometimes you can still see the satellite.
Right. But that's not where the sun is. It's actually down lower because of the whole bending as it goes through the atmosphere thing. Just like when you look in the pool and you see stuff in the bottom of the pool, that's not where that stuff in the bottom of the pool really is. Same thing here with the sun. Okay?
So like my grandma always tells me about like the green flash and stuff. Is that when like the sun is like at the perfect angle that you see green? Or
I'm not
does
familiar
that
with-
have anything to do
I'm
with
not familiar
it?
with the green
Has
flag.
to be.
You're not?
Look it up.
Yeah.
Wow, recording.
I swear he's not flying green.
That's fine. I've never heard it.
Can we look it up?
Seriously?
So, are you okay? I honestly cannot help you with that. So.
What is it?
All right.
It's like when the sun
So
is-
here. Sorry. Sorry. Are we good with why things look certain colors?
Yeah.
Okay. But then it depends not only on the color of the object. These blocks are all these different colors because red reflects off this one, and orange reflects off this one, and yellow reflects off this one, et cetera, et cetera, et cetera, et cetera, et cetera. But that's only because we're shining white light on it. And white light has all of those colors in it. But if we look at a different picture, like here, if we only shine red and blue light on these blocks, what happens? What happens to green?
Black.
Green turns black.
Black.
It's supposed to be black, so colors aren't
Blue
pictures
turns
are best. Okay. Because blue's still blue and red's still red, right? But green is black. Why?
Because
Green or
there's
green.
different colors.
What do green things do?
Reflect green light.
Absorb.
There's not
Reflect
green light.
green light.
Green reflects green light. If there's no green light, it doesn't reflect anything.
And why doesn't orange and yellow and blue and purple do that?
Orange and yellow and blue and purple are sort of combinations of those other sort of colors of light. They're like mixing different things. So here, these sort of reflect a combination of red, blue, and green.
Since red, yellow, and blue are like the primary colors.
Red, yellow, and blue are primary colors of paint, but not for light. It's a little bit different. I know that sucks. It's the way it is. So. But then here, right, if we bring green light back, what happens to the green block? It's green again,
But the
right?
blue turns black.
But, right, the blue and the purple now, if we take away the blue and the purple light, purple now turns black because it's not reflecting anything. So we had our discussion, right, from Friday about whether you can see stuff and whether you can't see stuff. All right? Based on that discussion, black things, well here, this block is yellow, or this picture of this block is yellow as it's projected on the board. What does the board do?
It reflects
reflects
light.
the light.
How much light does the board reflect?
About all of it.
Because what color is it?
White.
It's white. It reflects everything. So here, what color light is shining on this block right here?
White.
Yellow.
Yellow light is shining on this part of the board. Because here, the projector is projecting yellow light. Yellow light bounces off of this part of the board and comes back to your eyes, and you see yellow. What color light's reflecting off this part of the board?
Red.
Red, because the projector shines red light from that part. It bounces off the board and goes to your eye. Okay. Now, will that part of the board always be red?
No.
No, it depends on what color light shines on it, right? Or what color light doesn't shine on it, right? It's really hard to just hold this thing still without looking at it, right? Right? So now,
It's still red.
what color is the board?
Oh, it's black.
It's white.
It's still a white board,
Oh.
but
Oh.
what is it looking like to you?
Black because there's an absence of light.
There is no light hitting that part of the board. So it looks black to you, not because the board changed its composition, but because there's no light shining on that part of the board.
But still a white.
It's still a white board. Okay? Lexi, go ahead.
So if it wasn't a whiteboard, it was like a blackboard with all the stuff you just.
Now, in theory, yes. But remember, Lexi, going back to this picture. Not this picture. This picture, right? We said that whenever there's a change in medium, what happens to some of that light? Some of it gets reflected, right? So even on a black board, you can still see some light coming off of it because some of it reflects off of it.
So does
And
this
so that sort of depends on what it's made out of, right? Like here, I put this up here, you can still see things that are on it, right? Even though it's a black piece of paper, because some light reflects off of it, okay? But if you had something that was really good that could absorb all the light that went on it, yeah, it would look black regardless of what you would put on it.
so is like all this color stuff like a theory or a law?
This is definitely, well, the law is that red light reflects off of red things, blah, 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 blah. The theory, the explanation is that the red color that makes something red absorbs all the other colors of light and reflects red. Does that make sense? Because it explains why it happens. Now, going back to that, right, in the summertime, what are you not supposed to wear outside in the summertime?
Black.
Black shirt, right? What do black things do?
Absorb light.
They absorb what?
Light.
They absorb energy, right? In the form of light in this case. Generally, when energy gets absorbed by something else, what does it turn into?
Heat.
Usually it turns into heat, right? That's usually the best answer for anything when energy disappears, it turns into heat, right? So, if your shirt is not reflecting anything, right? What's happening to it all? It's absorbing everything, right? But a white shirt does what? A white shirt reflects everything. Okay? We're ready for an increased degree of difficulty question?
No.
Come on.
Let's do it.
So, if you gotta wear a color of shirt, what color shirt should you wear?
Right.
If you can't wear white or black,
Yellow.
if you have to wear a color of a shirt,
Red.
what color should you wear?
You should wear red.
You should wear green.
White.
Red indigo.
You can't wear white.
Did you just choose?
Can't wear white. You gotta wear a color.
Purple.
Orange.
Red.
Definitely.
Any of them.
Unlikely.
Just one of them.
Like a white shade of whatever.
It has
A
to be
baby
any
blue.
one of them.
It has to be a lighter colored of any of them, because then the shirt would be made where it's just little swatches, so it looks like it's lighter.
Wait, what?
If you have to wear a color of shirt.
Does it matter?
Yep.
Wait,
Give us the answer.
So,
Wait, is it red?
Green.
No.
it's one of these six.
It's violet, 'cause it's the lowest. It's the longest.
How about
No, it depends on what reflects the best.
Blue.
Oh my gosh.
what is it?
Out of anyone.
Oh, the colors don't exist.
Depends on which one I can't have.
Correct answer is,
The first
you should wear,
Yeah!
I said that a few
I
times.
got it right.
yeah, but then you said orange and yellow too.
Yeah.
I said them all.
So, why purple?
Because it'll absorb the colors the most and turn black. Wait, was that
Okay, you
It has the shortest wavelength.
Okay, so, purple shirts reflect purple light, right?
Yep. Oh, and there's not a lot of it.
What do you know about purple light?
It has the short
If
wavelength.
it has the shortest wavelength, that means it also has the highest what?
Frequency.
And high frequency electromagnetic waves have more what?
Bends in the mode.
Just kidding.
Frequency.
Bends a lot.
High frequency electromagnetic waves
More energy.
carry more
Short
energy.
wavelength.
So, high frequency, short wavelength electromagnetic waves carry more energy. So if you've got to get rid of all the colors except one, right? Get rid of purple. It's the highest energy
Okay.
reflected off of you. Which color of shirt, right, would probably be the worst one to wear? Red, right? Because you're reflecting the longest wavelength, lowest frequency. Red is the least energetic color. So you're getting rid of it and holding on to all the other high energy colors.
Still
From
out of
the art
anything.
standpoint, it's like the closest
I mean,
color.
white would be the best, but if you have to wear a color, right, if you have to wear like a uniform or something, purple is usually the best to wear. Because it's the highest energy and you're getting rid of that high energy. What? Because we said, Paige, when you absorb all those colors, they turn into what? Heat. So if you're getting rid of the highest energy waves by reflecting purple, there's not as much heat. Okay? Well, so, you want it cool, but not too cool. So,
Yeah.
yes, Sam.
Is that when you get like hot and cool colors?
Kind of, yeah, although if you think about it, right, like, you know, I guess, yeah, kind of, but like red, you know, if you're things that are red, we think of more as warm, right, and that they would be warmer than things that are blue. I guess so, I never really thought of it that way. Alright, so, the rest of the slides, the ones on primary colors of light, secondary colors of light, complementary colors, and colors of pigments. Don't worry about those 4 slides. They are not going to show up on your test. They are on your objective sheet, but I didn't put any questions about them.
Secondary colors and primary colors.
Secondary colors, primary colors,
Will
complementary.
they be on our file?
They're not on. What?
If it's on the test case.
Well, he needs to define anti-negative.
Very good.
Oh yeah, is that like when blue stars are the hottest because they have the highest frequency light waves?
And red
Yeah,
stars
okay.
are the coolest.
Good.
Okay, so by the way, the green flash happens at
I've actually
It was in a
heard
movie
that.
too. Like,
Wow.
Some movie.
they talked about it in a
Night of the
movie.
Comet?
And my
Alright.
grandpa talked about
So-
it.
Well, I had a real question.
Hooper, question, go.
Can you define nodes and
Okay, so
Really?
nodes and antinodes. So, actually, let me do this, alright? Test tomorrow. Test tomorrow is 32 total points. Okay? So it's a little bit less than the previous test. Okay? I wouldn't say that.
You said the last one was.
Yeah, but apparently I was wrong. So 32 total points. There are a lot of new definition words in this section, so make sure you know your definitions. There's a couple of things that we did in class that I told you probably you should see again, right? I gave you one of the short answer questions a couple days ago, right? Also, on Thursday, I think, we went over a certain part of the quiz, right? I made us focus in on a certain part of the quiz, so make sure that you look at that part of the quiz there, okay? Fish, go ahead. No, the picture on the back side. Okay, Fish, go ahead. Okay, so as far as the questions go, you got your multiple choice. You're going to have a couple of short answer questions. There are a couple of what I would consider to be pretty straightforward calculations, very similar to what you had to do on the quiz. Okay, so make sure you understand what's going on there. Okay, there is actually 2 short reading selections on the test. I found 2 that I liked, so I put them both on. And
Why do we do reading sections on a science test?
did you take the practice OGT last week?
I didn't.
Wasn't there like a couple of sections that you just did?
Yeah, we'll take that next year. Start that next year.
Yeah. Why did you take those this year? To practice.
Yeah, so start more next year. So don't
You can do more next year, but we're starting now. Cooper, go ahead.
Can you define nodes and antinodes?
He did actually ask that.
Wait, no, it's
I
not
asked that
both of those.
during
Okay,
the first
so-
test.
Right, here's our medium when we make a wave.
Yes.
Okay? A standing wave kind of looks like this, but then real quick it sort of shifts so that this part that was down or up now goes down, and this part that was down now goes up. It just sort of like goes back and forth, back and forth, back and forth, back and forth.
It's like a seesaw.
We did that like here in class. Yeah, and we also did it down in the PAC too, okay? At this point right here, okay, if you watch the medium, if you watch the spring, it doesn't move. The parts around it sort of move, but there's one section where there is no movement, okay? What's going on? What did we say was going on at that point?
It's interference is
What kind of interference?
destructive.
Destructive. This is a node. So nodes are where destructive interference occurs. Okay? It just so happens in a standing wave that the frequency of the waves going down this way and then interfering with the waves coming back this way, the destructive interference always happens at the same point. And that's why we get the medium not moving, and that's what we call a node. Okay? But we talked about these parts right here. Okay? They're a lot bigger than the waves that I'm making, meaning what's going on at this point.
Constructive.
That's constructive interference, and we refer to those sections as the antinode. Okay? It just so happens that the waves traveling this way interfere with the waves traveling this way, and that the constructive interference always happens at the same point, and we call that the antinode.
Right.
Okay? Page, go ahead. Does it relate to this or something different? Hold on a second. Anybody have any questions based on standing waves? Okay, Chuck, go ahead.
So technically, on every single wave that you draw, there's always an antinode and node.
Yes, but not every single wave that I draw represents a standing wave. So some of them are just waves that are traveling through. If you draw a standing wave, then yeah, it has
Then you
antinodes
have
and
to have
nodes.
both
Yeah.
sides.
Yeah.
Like,
Paige, go ahead.
It says define the following terms and identify non-sketch
total of 1 second, then you could figure out the frequency from that. That would be the period. But if I show you 2 full waves and say this wave or this picture represents 1 full second, that would be 2 waves in 1 second. That's a frequency of 2. Does that make sense? Then I either have to give you the frequency straight off like I did on the quiz, or I'm going to have to say this picture represents a certain amount of time, so that you could figure out how many waves are there in that amount of time.
Okay, and then it says relate it to different types of waves.
The idea with the longitudinal versus the transverse wave. Longitudinal waves, the compression wave, you're looking at compression to compression to compression to compression, whereas in a transverse wave, it's crest to crest to crest to crest. So it's the same thing. It's the same, like wavelength is the point between this wave and the next wave. It's just, is it a crest to a crest, or is it a compression to a compression? Okay? Oh, go ahead.
For the Doppler effect.
Yep.
Can you explain how it changes?
Sure. I thought of a good example earlier today, so I'll give you that example.
Sounds like a plan.
All right. So here's a guy, and here's another guy, and got it. Go ahead. And here's another guy, and here's another guy. Okay. So let's say that they start, and they're going to run a race, and this guy starts 10 meters in front of this guy, and then the last guy starts 10 meters in front of that guy. Okay? They all can run at exactly the same pace. They all can run at exactly the same speed. So if I start them all at the same time, right? Gun goes off, all 3 of them start running at exactly the same time. Are they ever going to get closer to each other or farther from each other?
No.
Okay? So this would be like, this is no Doppler effect. This is just waves traveling through a medium, and you are the same distance away from where they started to where you are. Okay? They get there at exactly the same intervals. Okay? Oh,
It's that commercial about what's better, doing one thing or 2 things. 2, I can wave.